we're going to look at transformations of logarithmic functions. Before we start doing this work, let's just explore this function. So this is the parent function for y equals log base 2 of x. You can see that I can change the base of the function here. So we're starting with base 2. And remember, this is the inverse of y equals 2 to the x. So the exponential function, something we're familiar with. And, inverse interchanges the input and the output. So I think a nice way to think about this, an easy way to think about this, make sense of it, is to think about this as the inverse of the exponential function. And that means that if I interchange the input and the output, my input is now y and my output is now x. So if I put 0 in for y, 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16, and so on. But the logarithms are the inverse of that. So that's why it looks like this instead of a normal exponential function. Instead, when I put in 16, I get out 4 as the exponent. Again, if you're thinking about it in terms of exponential functions. Okay, or I put in 8, I get out 3. I put in 4, I get out 2. It's a nice way of thinking about it. It's a nice way of relating exponential functions and logarithmic functions. So the transformations are, as always, what we would expect. If I change a, it's a stretch. Okay, and so I can see that point stretching up. I can see that this point doesn't move when I stretch it this way. I can see, whoops. Let's do the k value change. We're not going to see a lot of k value changes, but you can see that as k gets bigger, it compresses it. As k gets smaller, it stretches it, as we would expect. C does not stretch or compress the points, so in relation to each other, they don't move, but they move left-right, and then obviously D is going to move them up and down. Let's see if we can get a better picture of that. There we go. So just like we would normally expect. In terms of trying to graph it, where the points move, again, quadratics are very simple with this. That's why we start with quadratics as the first function that we explore in terms of transformations. Where their points move in relation to the vertex is very straightforward. With logarithmic functions, similar to exponential functions, it's not quite as straightforward. So I think some of the work here is coming to terms with how the points move in relation to each other and how you find 2 or 3 points to be able to graph the function properly. So let's, so one thing I want to take a look at is this point. It's red for a reason. When I stretch, it doesn't move anywhere. When I do this stretch, it does move. That's not helpful. Even if I stretch it, the C value still just impacts its original location. So it's like the vertex of a quadratic function in that it's only impacted by the shifts, if we ignore k for now at least. And a vertical stretch does not impact that point. So it's a nice anchor point to start with. Okay, so we're going to look at that as one of our points that we can kind of start with, and we're going to look at the asymptote in a moment as one of the points we can start with. And then we're going to remember that changing the base is not transformation per se. Changing the base of an exponential function or a logarithmic function, really you're changing the parent function. You're changing what you start with and then transform. But these parent functions all have similar set of characteristics and properties. So we do think of them all alike. We don't exactly handle them as different parent functions the way we would quadratics and absolute value and that sort of thing. They're very similar, they're related, but when I change the base, not technically a transformation, it's a change of parent function. So just keep that in mind. And the textbook that we work with, for whatever reason, likes to work with base 10, which makes it tricky because base 10, you can really only fit 2 nice points on the graph. And so that makes it hard. So what they like to do is map those 2 points using a mapping formula and then find where those 2 points are and try to relate them. Not exactly the way that I like doing things, but in this case it works fine. And like I said, today is about coming to terms with how to find a couple of these points of their location and graph from there. So let's get started. So we're going to graph this function. We'll start with the parent function. So we have a relationship. Notice that it is base 10, okay? And so we'll start with that parent function. So 10 to the 1, 10 to the 0 is 1. And again, remember, we're interchanging our input-output. So that's my point there. And then 10 to the 1 is 10. So there's my other point. And I have an asymptote at y equals 0. Sorry, x equals 0, the y-axis. And we're going to talk about that in a moment, why that's an asymptote. And I think that that's a helpful thing to think about. In fact, in terms of the rest of this unit, it will be helpful, but also in terms of graphing. Okay. So we have we are supposed to state the transformation, so we can do that as we go. So we have a vertical stretch. It's been a while since we've done this. By a factor of 2. We have a horizontal shift. That's left 1. And we have a vertical shift down 2. Okay, so remember what we said. This point is not impacted by a stretch, a vertical stretch, horizontal stretch, but we're not really looking at those. So a vertical stretch. So I can take that point and just apply the shifts. And that means it's going to go left 1, down 2. And there's 2 different ways you can think about it. The textbook really likes using the mapping formula and just taking these 2 points. Where do they map to? Use those 2 points. Probably think about the asymptote again. We'll talk about that in a moment. And graph it that way. It's not my favorite way of doing it. It certainly works by just mapping those 2 points. But the way that I like, that I just think provides a bit better understanding of the growth in the graph in general, is when I increase this distance by 1, I'm going to increase this distance by a factor of 10. So if this increases 2, this will be 2 factors of 10, which is 100, goes off the graph, so we can't see it, but that is the logarithmic function. A vertical change of 1 corresponds to a horizontal factor change by the base of the log, which in this case is 10. So if I use this as my anchor point and I think about the vertical stretch, typically going up 1 would go over by a factor of 10. So instead I go up 2 and over a factor of 10, which would put my next point right here. So I went up 1, 2, and then I went up from this position, I went up 10, right? Because I've moved my point to the left 1, so that's why I get to 9. And then I want to talk about the asymptote. So the asymptote of the parent function is x equals 0. It's the y-axis. And so why is that, and why is that impacted by the horizontal shift? So let's just revisit this idea, okay, of of logs and rewriting them as exponents. So log base 10 of 0 equals x, or let's say equals a, so we don't get confused with x in the graph, means 10 to what exponent will give you 0? Well, that's not possible. There is no exponent that will give me a value of 0. And similarly, we've talked about this. What about -1 or -2 or any negative value, -0.01? 0 is the limit that it can get to. So anything 0 or below, we can't, there's no exponent that we could raise 10 to or any base that's going to give us that value. So that's why for the parent function, it's never going to exist in this area. It's never going to hit 0, and it's never going to go below 0. So asymptote, which means log base 10 of whatever goes in here can't be 0. So we see that in this case, it's x plus 1. Well, what will make x plus 1 equal to 0? -1 or anything below that. So that's something that we're quite familiar with, is thinking about this bracket, what will make it equal to 0, and then anything that will make it 0 or negative, that's our asymptote. That's where this graph will not exist. So it's a good way of sort of thinking about really the horizontal shift is going to give you the asymptote. But again, as always, understanding why is a good way to go. So that means our asymptote is at x equals 0. And I should have made that red, but anyway, and I can now graph my actual function. So this is f at x equals 2 log x plus 1 minus 2, the red graph. Okay, and let's see, so determine where the points go. Question 3. So my mapping formula is going to be something like this, x to y. Again, this is what the textbook likes to do. So the x values just went down 1. So it's x minus 1. And then the y values were multiplied by 2 and then subtracted by 2. And that will work for that point. So this point over here did start at 10, 1. So if I multiply 1 by 2, I get 2 minus 2 is 0, and that's where it went to. So it moved to the left 1 and then down 2. Right? So it does work. It will find those 2 points. It's an easy way to do it. It just doesn't help us understand the actual function a lot. It just kind of generates the graph. Okay, so the 2 points it wants us to map are 1, 0, and 10, 1. So 1, 0 goes to 0 and -2, and 10, 1 goes to 9, 0. And we'll do our domain and range. This is good. Another good thing to think about the nature of the graph. So domain, x is an element of the real numbers such that x is greater than -1. And the range, y is an element of the real numbers. Y can be anything. It's an inverse of the domain and range of the exponential function. So again, you can always think about that. That's always a good way to relate it back to something that you hopefully understand better. Let's take a look at one more. So this one again has a horizontal shift, a vertical shift, but it also has a reflection. Let's graph our parent graph. And the transformations. So that's a reflection in the x axis. It is a horizontal shift left 5 and a vertical shift up 3. Okay, we can do our mapping formulas, but let's think about what a reflection will do. A reflection will not move that point. It's going to stay in the same place. So again, the A value doesn't impact that point. A reflection will take this point and reflect it down to there, and then it's going to move over to the left 5 and up 3. Let's do this point first. 1, 2, 3, 4, 5. 1, 2, 3. Our asymptote, when I look here, okay, -5 in for x will not work. What happened to my point? Whoops. 1, 2, 3, 4, 5. 1, 2, 3. Okay, so again, my asymptote. If I put -5 in for x, that's not going to make sense, right? And so -5 and below is what this graph could never be. It's reflected, so it's curving the opposite direction from our parent function. And from here, instead of going up 1 and then over by a factor of 10, I'm going to go down 1 and over by a factor of 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is from here down, reflected down here, and then over 1, 2, 3, 4, 5, 1, 2, 3. Whoops, counted wrong. So 1, 2, 3, 4, 5, 1, 2, 3. There we go. Right? Instead of up 1, I go up 10. Okay. And I've got my 2 points. And that's about as good as we can do when we're graphing a logarithmic function with a base of 10. And let's see. X, Y goes to x minus 5, and then -y plus 3, which means 1, 0 is going to go to 1 minus 5 is -4, which looks good. And then -0 plus 3 is just 3, and that looks good. And then 10, 1 goes to 10 minus 5 is 5. And 1, so -1 plus 3 is 2. So 5, 2. Do our domain and range. We'll just talk about this quickly again before we go. But x is an element of the real numbers such that x will be greater than -5. And range, y is an element of the real numbers. Okay, so there we go. Something that's interesting, and again will be useful later on as you're graphing. What is the purpose of graphing? It always comes back to just understanding the nature of the function, understanding the nature of how the input impacts the output. What's the point of domain and range? Well, what kind of input does this function have? So when it says my domain is x must be greater than -5, that means this function, or this expression, if I just think of it as an equation or something as opposed to a function, won't take an input below -5. I can't put -6 in there. It doesn't make any sense. That's something that's going to be very important, in fact, in the next unit, maybe even more than in this unit, where we start really thinking about domain and range and possible values that will work in expressions or in functions. So that's something that's really important to think about. So what would change the domain is, again, something that you could think about as you're working through this. What kind of transformation would change the domain? That's something that you'll probably see, but not just like that's maybe an easy question to answer when you just think about the k value. What k value would change the domain instead of greater than -5 to be less than -5, let's say. But why? Like, how does that impact the input that this function will take? when you think about what the log function is and relate it to an exponential function. That's something that would be good thinking and good understanding to go through while you're doing the practice and doing some of this graph.